Hello, this is Dr. Liu. In this video, I will explain how to do differential calculus. This is a pretty short introduction. Its intent is for introductory physics students to kind of catch up on the content while they're still taking Calculus 1. So what exactly do we need for differential calculus? This is the reason we need differential calculus. We need to calculate rate of change, actually rates of change. There are several things we have already introduced in the one-dimensional kinematics that are exactly what that is, rates of change, such as velocity, right? Velocity is rate of change of position, so that's that. And we also know acceleration. And that's rate of change of velocity. Okay, so rate of change is like this. V is the change of position over change of in time. And acceleration, change in velocity over change in time. So the rate of change is just, it's simple. If you have a very simple relationship between the position and the time, say if position changes linearly with time, we just have a straight line and the rate is a constant. And that would be the same if we had a constant acceleration, then the rate of change is a constant. But that's not always the case, so we'll have to understand when the rate of change is not a constant, how do we obtain the rate of change? And I want to leave some space here so I can later write what this is going to be when it is not a constant anymore. So we understand the rate of change as slope of a line or curve. And the slope is calculated from what? Rise over run. Okay, so that's how we're going to investigate and try to understand how to take rate of change when the rate is not a constant. So let's switch over to our graphical presentation here. You can see there's a lot of functions we're going to go through, and I'll take a moment to disable all of these except for the first one. Okay, so this first one is just very simple. Function f of x is x, so this is just a very simple function with a slope of 1, and I'll use this assistant here as tangent. I can actually draw a tangent line. See there, the tangent line is actually the same as this line itself, and this green rectangle triangle is giving me rise over run. So the horizontal, I can't really point because this thing actually is locked onto my pointer, so if I try to point, it moves at the same time. So just look at the bottom, the blue bottom that says 1, because the program always wants the run to be 1. So rise over run is just rise itself, right? And the m on the vertical line, that is just the rise, and at the moment is equal to 1, right? So it is the same everywhere. So the rate of change is the same as 1. So if you put a number here, so I don't really want to write just in case it doesn't recognize my handwriting. So 2, for example, 2x. So then, as you can see, if you put your cursor somewhere here, the rise is twice as tall as the run is wide. So now you have rate of change 2 over 1, which is equal to 2. Very simple, right? This program always takes run as equal to 1. So it's still a constant. All right. So now let's think about something else. Let's put this one back to x equals fx equals 1x, and we'll enable the next function, which is a quadratic function here. Let's see, although it's small, right? It's a quadratic function. So the rate of change is no longer a constant because it's a curve. So let me put my cursor here. See, at the bottom, at the origin, the rate of change is 0 because if you draw a tangent line only touching one point on the curve, then it would be a horizontal line. But if you keep drawing that line as you go and travel along this this quadratic, and you can see the rate of change actually changes, right? It becomes more vertical as you go to a larger x value. We're not looking at the value yet. We're just looking at the trend. It also gets more negative vertical as you go to the other side. So we'll just focus on the positive side. Okay, so let's keep this in mind. Our x is equal to 0 at the origin, and the rate of change or the slope. Let's go back to slope. That's a one word, easy. So the slope is equal to 0 when the x is equal to 0. What about when x is equal to 1? Okay, let's go over here. Okay, so when x is equal to 1, how do I read x equal to 1? You just have to eyeball where my cursor is and go vertically down to that right there. That's x equal to 1. You can also look at the bottom left corner. It's hard to point and not losing the location, right? This is x and y. So the x equal to 1, this will be equal to 1. So let's move that back. Alright, so x is equal to 1. What about the rate of change? Is equal to 2. Okay, so what about x equal to 2? Okay, I'm going to move up here until I get x equal to 2. Oh, the rate of change is 4. Okay, x equal to 1, rate of change is 2. Let's go back to slope. And x equal to 2, slope is 4. What about x equal to 3? It slopes a 6. Okay, so we're going to rescale the y-axis to show some more. Okay, so x equal to 0, slope is 0. X equal to 1, slope is 2. X is equal to 2, slope is 4. Looks like we're doubling whatever x is. X equals 3, slope is 6. X equal to 4, slope is 8. I can keep going. How far can I go without losing that display? Okay, 5. X equal to 5. The slope is equal to 10. It looks like the slope, well, although the slope is changing with location, it is related to the x. It's twice the x, right? Okay, so that's good. Let's write that down. All right. So for a line, let's say y of x equals ax. Slope is equal to the a, this factor right there, and I showed a equal to 1, a equal to 2. It doesn't really matter. It's a constant. Okay, and what about quadratic function? Now we have y of x equals, what we actually had was just x squared, right? X squared. So I'm going to leave some space here, and we can explore that just in a little bit. And what we found out was the slope is twice of the x, right? When x is equal to 0, slope is 0, x equal to 1, slope is 2, right? So the rate of change, the slope, is twice x. So slope is equal to 2x. And does it matter if I have a factor like an a there? Well, we can try that. Let's go over there to the plotter and try. So now we have this x squared. So let's do maybe a 3x squared, 3 times. Okay, 3 times x squared. So does the 1 to 2 ratio still maintain? What I meant was 1 to 2 ratio was the slope is twice the x value. Okay, so let's see, x equal to 1. Okay, so now well, the slope is equal to 6. So it's no longer twice, it's actually 6 times, or the 3 factor times 2 times. Okay, and x equal to 2, here the slope is equal to 12. So that's still 6 times. The 6 comes from the original 2 times we discovered, and then multiplied by the 3 factor I threw in, right? Okay, so over here, this is going to be a little difficult. I have to scale this further down. Ooh, 3 and 18. All right, so let's see, that's 6 times, right? The 2 was from the original observation of y equals x squared, and then multiply the 2 by 3 because we threw in a 3, right? So that's what this is doing. This is also 6 times. Okay, so now we understand the factor in the front is also going to be affecting the slope. So that's the case. If I write a more generic expression here, the slope is going to be related to the a and also twice a x, depending on where x is, right? When x is equal to 1, this is a 3, for example, a 2, and the slope is equal to 6. When x is equal to 2, the slope is equal to a 12, right? So we had that as 3 and then 18, 4 and 24. So and that gives us an idea how to get the slope of a quadratic. A quadratic is well, the factor times this square somehow is represented here. Okay, so let's do maybe another expression. So let's switch over to our plotter. So we'll get rid of that and move on to another function, which is 1 over x. We'll go and scale this back, and we'll get rid of that. Only go and look at 1 over x. So 1 over x, let's see, the slope was actually vertical, very high, and it gradually drops, right? Gradually drops to about 0. Only reaches 0 when I have to move my cursor really far away, right? So that entire thing is a negative slope. Okay, so let's remember that the entire thing is negative slope. And let's now relate the quantities together. Okay, apparently if I am here, x equal to 1, the slope is equal to minus 1. Okay, let's just remember the minus and only read the magnitude for now. And what about when x is half? Okay, and m is actually 4. Okay, so not easy to understand. What about x equal to 2? Well, the slope is actually a quarter negative, equals 3. This is actually 1/9. Okay, 4. This is 1/16. So it looks like it's actually squaring the 4 and putting it in the denominator. It's like you take the 4, right, and you square it, you get 16. And then you put it in the denominator, it's 1/16. And then you slap a negative. Okay, so that is the slope of a 1 over x. It seems like there's a negative. There's also 1 over x squared. Right, so that's the slope right there. Okay, so now let's move over to the notes, and we'll just have y equals 1 over x, right? So the y, the inverse function 1 over x, and the slope is equal to, there's a negative and also a square of x in the denominator, right? I had a 4 and then the slope was 1/16 negative. Okay, so let's see, 1, 2 more. Okay, so let's get rid of that and look at another one. Okay, so this function is the exponential function of x. This is a very interesting, and if you want to say strange function, if you want. So the slope apparently starts from 0 and it grows gradually into about infinity. Okay, so everything is positive slope. All right, and let's look at the value, how the value is related to the location. Okay, so okay, when x is equal to 0, slope is 1, and well, when x is equal to 1, hard to get to the 1, slope is 272. Okay, it gets a little difficult to understand how these things are related. But if you look at the y value, well, how do you look at the y value? I'm gonna have to move really carefully. Okay, here outside, and right here, it doesn't have the display right here. So let's have a display the value, and now you have the display value. So x and y. I want you to look at the y value right here, and compare the y value with the slope. Okay, so now y value is equal to 1. The slope m is also equal to 1. Increase a little bit. Okay, y is 149. Well, the slope is also 149. That's strange. Okay, y is 201. Slope's 201. So y is 272. Slope is 272. If I can hold my pen without moving it. And y is 406. Slope is 406. So this looks like the slope itself is the same value as the y value, or the exponential function of x is the slope of the exponential function of x. It's kind of difficult to describe otherwise if you are not showing the values. So here's an exponential function. We'll have y of x equals exponential function of x, and the slope is the same as this y function itself, e to the x, because we just checked the slope values are exactly the same as the y values. The y is this, right? This is y, and that's y is equal to, so that's y, right? So that's an interesting function. You can also check other functions. For example, I have this set up, but I don't really want to go through this because I want to keep the video short and the topical. I have a natural log. Okay, I have a natural log of x, and you can explore what this is going to be. 1, x is 1, slope is 1, x2, slope is half, x3, slope is 1/3. Well, you get that, right? X is 4, slope is 1/4. You get that. And there's also other sine and cosine functions. So you can explore this on your own. I'll provide a link to the program, and you can add any functions you like. So let's now return to our notes. So these functions, what we can call them, they're all polynomials, right? X to a certain order. So let's put on the right side. Let's say y of x is a factor a, x to the nth power. So that covers all of these. And how does that actually change? Slope is a constant. Okay, so slope is a. Okay, it looks like x is gone and slope is this a. And if I have x to the second power, so I'm looking at this line compared to that line at the moment. So what happens? A always stays in the slope. Correct. Okay. And also the 2 here, power of 2, seems to be appearing as a factor. And that also works here. The power of 1 appears here as a factor. Correct. And then what happens with the x? X is the first power. Now x actually goes down to the 0th power. Anything 0th power is equal to 1. So this is just a 1. And then x to the second power becomes what? X to the first power. So we're basically doing several things to get slope from a polynomial term. One thing is the factor in the front will be included as part of the slope's factor. And then the next thing, the power of that polynomial becomes a factor that is multiplied into the existing factor. So this 1 power or 2 power. And then the third thing, the x to whatever power, it drops down by 1 power, 1 to 0, and 2 to 1. Okay, so let's see if that actually applies over here. I didn't have an a there, right? I didn't have an a there. But I can still say that, well, okay, a could be included. I just didn't have that. So if I follow the same exact rule, I first move the a around. So, okay, the a is equal to 1. Okay, a is equal to 1. And then the second, I take the existing power and use that as a factor. So the existing power right here, This is x to the minus 1 power. So I'll take out the minus 1 existing power and include that as a factor. Oh, it's right here, minus 1. It's already here. And then the third thing is I take the x and drop the power x to 1 less. 1 to 0, 2 to 1, or minus 1 to what? Minus 2. So this is actually minus 1, x to the minus 2. So that actually fits. And if you throw in an a, it'll just show up as a factor besides the minus 1. So this actually, all these imply the same exact rule here. So the slope is, well, a is included, right? The factor is included, and the power of x is included, and then x power has to drop by 1. So that's the rule. And we'll call this a differentiation. So as is dy, y is a function of x over dx, and the dy over dx, you can get rid of the intermediate variable called slope, is a n x n minus 1. All right, so we can do an example. If y of x is, say, 2x cubed, then what about the slope of that, or differentiation of that? Dy over dx is equal to, well, we keep the factor in front, and we obtain the power, and then we decrement the power, so 6x squared. That's how the slope of this is. It's going to vary like that. So as you can see, the slope is a function that has less power compared to the function itself. And it makes sense. Slope is rate of change. If you're not changing, then you have a constant slope. If you're changing, you have some sort of linearly changed slope, right? So it makes sense. And this one is an interesting one that we'll later encounter this. We can write it this way: because the exponential function is actually an infinite series of polynomials of all different orders, starting from 0 and up, you can actually derive it, but it's not our place. We're actually just reviewing math, not teaching it. So if I write this in a more generic way, actually, excuse me about that. So let's put x over here. And then the slope, or dy over dx, is going to be a e to the ax. So essentially this non-changing part, the function being its own derivative story, is maintained, except that there's a factor that drops out. And you can also do natural log, sine, cosine, but I think we have gotten enough, because the purpose of this introduction is to support kinematics in 1 and 2Ds, which is primarily just polynomials up to the second order. So I think we have done well enough. So what I want you to remember is just this right here. So the dy over dx, if you have this y, and you can do a lot of simple examples, just basically imagining that, and then you can do this differentiation. So one more thing I want to say about this: if you're doing differentiation of a sum of several terms, you can do them separately. So this is because of the linear operation of differentiation. So if I have an example here, I'm just going to have that right there included as one of the example terms, 2x plus 5. Okay, if you have a constant, then basically the rate of change is 0. You can also use this formula here, but it's kind of awkward that x to the 0's power, right? It turns into the minus 1 power. It only applies to these polynomial terms without constant. The constant has a 0 derivative, right? Constant doesn't change, no rate of change. So if you do dy over dx, that's actually d over dx is that operator taking derivative of a function with respect to x. 6x squared minus 2x plus 5. And you can expand that into 6x squared, taking the derivative, separately minus the 2x, taking derivative, and plus the 5 taking derivative. And applying that rule, we keep the 6 and we drop out the 2 and multiply that 6 with 2, so we have a 6 times 2. And x squared needs to decrement its power to x, and then we'll do the same thing here, the 2 and then multiply x to the first power, and x to the first power drops to x to the 0's power, so x to the 0's power, which is a 1, and then because the constant doesn't change with x, its derivative is 0. So if we sort this out, we have 12x minus 2, right? X to the 0's power, this is a 1. Okay, that's first part. Let's make that clear, and we'll do some lines. See, that decrements by 1, and that decrements by 1, right? And the factor is maintained, and the power is brought out as another factor, right? So that's how the rule applies. Hopefully this helps you understand differential calculus with the most basic expressions. Thank you.